Hello, welcome to this Vib Tip session. Today we are going to talk about two parameters directly involved in pulse synthesis from a given SRS reference, T-e and T-E. From shock response spectrum theory, once the Q factor is fixed, we know that the transient acceleration time history has a unique damage signature plot called SRS that represents the energy content of that time history trace at different frequencies within a frequency band. However, the inverse process of synthesizing a time domain pulse from a given SRS has 1 degree of freedom, so theoretically there could be an infinite number of pulses with the same SRS. From all of them, our controller tries to generate one pulse that can be reproduced on our shaker and which associated displacement, velocity, acceleration are within shaker's performances. Said this, several standards add an additional requirement to the synthesized pulse to make it more similar to the original time frames used to calculate the reference SRS. This extra requirement is related to the duration and the concentration of the energy of the pulse. Probably this process is more clearly described in Military Standard 810H Change 1, Method 516.8, Shock in Annex A. Based on my experience giving Military Standard 810 trainings and frequently asked questions, very often engineers face difficulties to understand the T-e and T-E concepts and apply the procedure properly. That's why I decided to issue this Vib Tip edition, including a practical calculation from a real measured transient acceleration time history. The figure below shows an example of a single shock time history identifying the 3 regions that the pulse can be split and the estimated duration T-e and T-E. The 3 regions are measurement system noise floor, the shock, and the post-shock noise floor. T-e overall shock duration is defined as the duration from the zero crossing from the first measurement acceleration above the instrumentation noise floor until the perceived termination of the shock. Here we see that the signal starts to separate from near zero, and then there's a time where the typical resonant ringing behavior of the structure response really decays to low G levels. T-E, concentration of energy duration, is the interval where the highest concentration of energy happens. We can see that is from this time to this time. Then, with the SRS magnitude controlling the synthesized pulse magnitude and both T-e and E defining energy distribution, the synthesized pulse should resemble the measured pulse while having the same SRS. Well, let's go to a practical example on the procedure to calculate T-e and T-E from a time trace. We start with an Xcel compatible format as .csv. Normally, all data comes in a single column. We adjust data to number format and place time in column A and acceleration in column B to comfortably use the Xcel tools. We verify that in this case, sampling rate is 10,240. Then, we plot the graph of the time trace, noticing that data mostly cover the active part of the shock with little pre- and post-pulse shock measurement. The shock duration T-e is defined as the duration from the zero crossing for the first measurement acceleration above the instrumentation noise floor until the perceived termination of the shock. Therefore, we analyze the first region of the signal looking for what could be considered the instrumentation noise floor and the last region of the pulse. We decide to consider a full scale level of 100 G. Decreasing minus 60 dBs, we define the noise level limit in 0.1 G. We add a column for T-e region. Checking the data, we realize that up to cell A70, the level is below 0.1, and we can consider row 71 as the starting point of T-e. To determine the end, we change the scale of the axis in the graph to zoom in from 1500 to 1600 milliseconds. We see that from 1550 milliseconds more or less, the acceleration level reduces very close to zero, and we can consider the termination of the shock. For further T capital E calculation, we end T small e at row 15,870, and therefore T small e is practically 1.5 milliseconds. That corresponds to 15,800 rows. The highest concentration of energy interval, T capital E, is defined as the minimum length of time that contains any time history acceleration magnitudes exceeding in absolute value acceleration peak divided by CF, being acceleration peak the highest shock peak amplitude, and CF is the crest factor, defined as the ratio between peak acceleration and the corresponding RMS values associated with the single shock. To accomplish this, the standard recommends to compute the crest factor in several intervals over the duration of T small e, for example 10 intervals, and get, for the previous formula, the maximum crest factor, compute on the individual intervals. Therefore, all amplitude less than the last amplitude greater than acceleration divided by CF max define a time between greater energy concentration and lesser energy concentration that is quite robust to characterize the shock pulse, and we use in our synthesized pulse generation. So let's divide T small e in 10 intervals of 1,580 rows each and insert an auxiliary column more for calculation. We filter first row and select interval equal to 1. Within this cell's range, we calculate RMS value using the Xcel function standard deviation of a large number of samples and the maximum absolute peak acceleration using the function max absolute. Then we divide the peak value by the RMS value to get the crest factor of interval 1. We execute the same calculation for the remaining 9 intervals, copying and pasting the same formulas since intervals have same number of rows. The maximum crest factor corresponds to 3.06 in interval 1. Then we calculate acceleration peak divided by crest factor maximum, that is equal to 18.65 g. This figure is the reference to determine T capital E duration. Checking the data, it's reached for the first time at row 278 and last time at row 2852. We color the interval in red and T capital E is equal to 251.5 milliseconds. Having established a nominal value for T capital E, the synthesis of a representative pulse shall have a tolerance between 0.8 T capital E and 1.2 T capital E. Summarizing, T small e and T capital E are important concepts involving both the original single shock used to define the reference shock response spectrum and the time trace synthesis process. Its calculation is essential to properly perform our SRS test. Well, thanks for attending, and let's meet in the next Vib Tip session.